Good evening, sir.
Hi, Dr. Sonic Kiran. How are you? Hello.
Good evening, sir.
Good evening. How are you?
Fine,
Must,
sir.
must.
Yes, sir.
Good. Just within 3-4 minutes, we will
Yes,
start the session. Okay.
sure, sir. Sure, sure.
Dr. Sonic Kiran, can we start the session?
Yes, sir. I'm
Are you
ready.
ready? Okay.
Yes, sir.
Hello, everyone. Welcome you all again to the last day of 1 week long ongoing Indo-Canada Spark course on dielectric resonators and its applications. Organized by National Institute of Technology, Silchar, in association with the Delhi Technological University, Delhi, and Queen's University, Canada. I extend my warm welcome to the first distinguished speaker of today's session, Dr. Sonic Kiran Kumar Das, who will start his presentation in continuation to the last lecture held on first day. Now I invite Professor Sonic Kiran to start the session.
Very good, Nick. Should I start sharing my screen?
Yeah, you can start.
So can you see my screen now?
Yes.
Is it okay?
Is it okay?
So is it visible, right?
Yes, yes, it is.
Okay, okay. So very good evening, good afternoon, and good morning. As we are from different time zone, and today I'll be continuing my that topic that I had given in the last class. That is some fundamentals of dielectric resonator antennas and their applications in engineering. So as most of the parts we discussed in the last class, but we just started the performance improvement techniques that can be done with the DRA. That comes in my part 2 lecture, that is today on 24 November. Okay. And about performance improvement, as we already discussed in the last class, that mainly if you look at DRA performances, it mainly depends upon its bandwidth, gain, circular polarization, and mutual coupling. And above these, out of those four technique, out of these four performances, we have already discussed those techniques that are associated with bandwidth. And today we'll be focusing on those different techniques that can be used for gain improvement. Okay. And some techniques like superstrate technique we already discussed, and today we'll focus on the one popular technique that is known as the reflector backed DRA. Okay. So first of all, we should have an idea about what exactly reflector. Okay, it's a common fact that each practical antenna, okay, when those go for real field application, they generally deal with some kind of unnecessary backload radiation. Okay, and because of that backload radiation, that lowers the gain and the directivity that is in the broadside. The gain of the antenna can be further improved by redirecting those undesired backload radiation in the direction of desired main lobe direction. Okay. The third part that comes that for avoiding the backloop radiation, a reflector plane placed below the ground plane could be a solution. And those techniques actually, that reference that I have given in 1718, those techniques have been used for not for DRA but for different other antennas. And we thought of to introduce this kind of superstate technique, sorry, this kind of reflector technique in our dielectric resonator antenna. And we can see the right hand side figure, we have shown the structure of the DRA. It is very simple. Just let me switch on the arrow. Okay. Okay. We can see on the right hand side, excuse me, this figure, this is a very standard DRA like slot coupling, okay, or you can say aperture coupled cylindrical dielectric resonator antenna. We have used simple microstrip line, and what we did here, we just placed a reflector below that substrate. We can see the fabricated prototype on the right hand side. Okay, and this work is actually done by us, and it was published in IT Microwave Antenna Propagation in year 2017. So let us move into the detail how we started designing of this antenna. So what we thought about before starting this work, we thought that we cannot place a ordinary reflector below this substrate. We need to have some idea about like how it will be helpful for checking the backlobe radiations, how it will be reflect, how it will redirect those backlobes, signals in the both side direction. So what is important, first we just did a small analysis. On the left hand side second figure we can see we just the same what is our antenna, we just put it in a form like we can see the first one that comes the ground plane layer, then we can have a air layer, then there is a reflector. Okay, this ground plane is nothing but this first this part. Okay, then there is in between we can see there is air gap, and the last one that is nothing but reflector plane that are also shown in this figure. And again bottom side of this below this reflector we can have again a air layer that is normally nothing but the atmosphere only. So what we see here, when there will be when the antenna is here, directly resonator antenna is here, and the microstrip line is given here, and it started coupling the energy through the slot at this point. At this moment what happens, some amount of energy also comes towards the back direction. Back direction nothing but the below direction, I mean it just moved to this air layer area. Okay, and when that moves to the ground I mean air layer area, it will definitely incident on a reflector. That reflector is nothing but it may be of different type of material, or even if we take here in this case we have considered a dielectric material or dielectric sheet, or we can say like normal FR4 in this case. We can also go for different other like archidural or something, and how that can be mathematically how we can calculate the losses that I will show. So this is nothing but as per the antenna structure we have designed. And if we look to the last figure, the left side down bottom figure, we have just for a clear understanding, we just differentiate this part into three parts. Okay, the part one will be the layer one, that is layer n. Then there will be layer n plus one. Then there will be layer n plus two. Let me just highlight pen. So this one is this layer is nothing but layer one. Then we can have this is air layer. Again we can have a another layer that is dielectric layer n plus two. Okay, if we'll just compare this figure with this figure, then this is layer n, this is n plus one, and this is n plus two. Okay, so the ratio of the reflected wave to the incident wave, because what happens when the wave started coming in this direction, then it will first incident in the this layer. This is the first layer where it will incident. Okay, so this is nothing but the air layer. So what happened when the ratio of reflected wave to the incident wave is given as, this is a very standard formula that we can find very standard. This is not any unique. Okay, that is this formula is available. So if we'll just look into this formula, we can have a idea about the ratio of reflected wave energy to the incident wave energy that can be calculated using the relative permittivity of different layers. Okay, from which layer to which layer the wave is moving. Okay, if the wave is starting from n plus 1, it is moving to the next layer, that is nothing but sorry, if the wave is starting from the n layer, okay, then it is moving to the next layer, that is n plus 1. That is nothing but this one is n plus 1 and this is n. Okay, and what is important in this case, that is the loss tangent we have noted here. Okay, what is the loss tangent? This loss tangent, as we know, when we consider any dielectric material, then it must have a loss tangent. Okay, and in this case, in this particular case, as it was our student project, we just thought about going for the normally available material, that is FR4. And FR4, that loss tangent comes around 0.04. uh, then we just put all this I mean information, whatever the like epsilon r we know how much, and for which, what is the next layer, what is the relative permittivity. Okay, then what we need to do, we need to find the ratio of amplitude of the transmitted wave to the amplitude of the incident wave. What happens, just look at this left side bottom figure. First what will happen, one wave will be incidented. Okay, then some part of that wave will be reflected back and some part of that wave will be transmitted. Okay, first we need to find the ratio of reflected wave to the incident wave, I mean between these two we need to find the ratio. Then what we need to do, we need to check the ratio of transmitted wave to the incident wave. So this is nothing but the transmitted wave. Okay, and this is the incident wave. We need to find the ratio between these two also. Okay, and what happens what happens, this transmitted wave, also keep in mind, when the wave is starting from n layer, then it's going to n plus 1 layer, then it is going to n plus 2 layer. Okay, so the wave that is transmitted into the n plus 1 layer, that is nothing but the same wave is nothing but the incident wave for the l- layer n plus 2, because there is no obstacle in between. Okay, so directly what is transmitted, the same wave will be incident over here. So instead of transmitting, writing uh, this transmitting wave, we can write it incident wave n plus 1 region. Hope you understand it very clearly, that there is no obstacle. What is coming here, the same wave is striking here. Okay, I mean the transmitted wave for layer layer n is nothing but the incident wave for layer n plus 1. Okay, then we can calculate this formula. This formula is also a mathematical formula that is already, that was already available. We didn't do much thing into this. Then what we did, then we need to find the power, because if you just the power, how we can find out the power, how much power is being transmitted, how much power is being reflected. To find that one, we need to use the Poynting theorem. Okay, we need to use the Poynting theorem, and then we can use these two formula for finding out the power in different layers. Okay, when we have this information, okay, how much power is being transmitted, how much power is being reflected for different layers. Okay, so once we have the idea about the power in different layers, the power level in different layers, by using the Poynting theorem, we can find the ratio between the power of different layers. That is nothing but Pn plus 1 upon Pn. So it is just giving a idea, I mean it is just giving the information about the ratio of power between two layers. Okay, and this is nothing but this that we used by using these two equation. I mean if we'll just uh, put this formula by this one upon this one, then we'll have this one. So in this case, if someone wants to find the ratio of power, because what happens, our main idea was that our wave was incident from here, and it is finally it is being transmitted from here. So what we need to do, we need to find the power that is available in this n plus 2 region. Okay, this n plus 2 region, then what is the power that was in Pn region. Okay, so what we need to do to find the power ratio of Pn plus 2 upon Pn, so this is nothing but Pn plus 2 upon Pn plus 1, this is nothing but n plus 1. Okay, and again this one. So by using this one, we finally can have an idea about how much power is being transmitted. See, the important thing is that what controls here, what kind of material we are using. Okay, so mostly if you'll see here, it totally depends upon the relative permittivity of the material as well as the loss tangent. However, if you see, the loss tangent is very much effective in controlling the power, amount of power, or that will definitely control the power ratio. And what we finally here, what we guess here, once the ratio, generally if the ratio generally must be varying between a positive number and maximum will be 1. Okay, so if something that uh, if we find any number that is that ratio is coming between positive number, let's say from zero point 0.1, between 1 2 and zero point 0.1, if anything that lies in between, we can say it is partially reflective surface. Okay, and in case we find that the ratio is totally 1, then we can say nothing has been reflected, everything got transmitted, because what we transmitted here, that we also find the same amount of power we found here. So there is nothing reflected back, and that is generally not possible. In case there is no medium in between, then of course that is possible. But in case we have the obstacles like the reflectors, or we can say dielectric substrates or reflector, okay, definitely we will find some amount, I mean some value that is between zero point 0.1 to 1. And of course, depending upon the loss tangent, the value may like we may find some value like zero point 0.5, we may find something zero point 0.6, okay, and zero point 0.7 like this. But in our case, we found it around zero point 0.6, 0.76 something, I don't exactly remember that value. So what we concluded, that our approach is may not be perfectly reflective surface, okay, but perfectly reflective, but it is partially reflective. Okay, it is coming at 0.76 the ratio. So we found, what we assume, that may not be 100% capable of reducing the backlobe radiation, but somehow it will be capable to reduce some amount of backlobe radiation. And once we excuse me, and once we After finally calculating the value, then we designed that same structure in the HFSS, and we can see here that if you'll see the S11 performance without reflector and S1 performance with reflector, what we found, the S11 performance is bit changed, but it's not, of course, if you'll see as overall, it is not at all. It's not, the change is not that much significant, but there is a significant improvement in the gain. The gain has increased. If you see, it's around five, more than 5 dB, the gain has been increased. So we find this technique and calculation is very much effective in finding sorry, in enhancing the gain of an antenna. The main part of this work was without disturbing the antenna structure, or with a very simple technique, because we did not use here any superstrate or something, just a simple dielectric reflector. The next thing, if you see, there is also another literature available in online. We can see some people have used metal reflector. This is a metal reflector actually. Okay, and the reflector shape is like a box shape. In case we our project, we did it a flat reflector, and we found some authors have done also in a box type reflector, and that is also being quite significant improvement in gain. We can see it's around also more than 2 to 3 dB improvement they have got. And the next one that comes, this was the probably the first structure, this kind of structure that we introduced. So it was published in RF CAT in 2017. So what we did here, we thought of that we have already know that by using this superstrate we can enhance the gain, and also by using reflector, by we can enhance the gain. So what we did, we just thought about, let's combine both the techniques, and we also did that, and we found also it is very much effective. We can see on the right hand side the gain curve, how beautifully that is showing the enhancement. The DRA alone is nothing but the black one, that is there is no superstrate and no reflector in that case. That is nothing but DR alone, that was giving again around 5 dB. And the moment we put another superstrate, so the gain was enhanced by around 3.3 dB. Sorry, the gain enhanced by 1.3 dB, and that was around 6 dB range. And also then also we just used only direct reflector without superstrate, then it was giving up gain around, we can see it gain around this blue line. Okay, I mean there is some enhancement. And when we just combined this technique, we found that this is giving the best gain, or we can say the peak gain of this structure. Okay, and this was around, if you'll see, the total enhancement gain is around 6 dB by using this structure. Okay, and this structure is very, analysis of this structure also very simple. The way we analyze superstrate, we need to analyze first using superstrate, and the way we did analysis for the reflector, we also need to do the reflector analysis. The thing is that we just need to combine this technique, and once we combine, we need to optimize this height also, because sometimes once we become, this becomes a hybrid combination, right? And once this becomes a hybrid combination, there will be some impact also, so we need to check these two heights, and that depends upon the which frequency we are working on. Okay, and the bandwidth is also not that much affected. So this technique also we can use, those who are using any antenna, this technique can be used for enhancing the gain. Okay, the next performance that comes for DRA is we know circular polarization, and almost most of us we know that what exactly is circular polarization and what is polarization. Polarization nothing but that describes the direction of electric field with respect to time at a particular free space. It can be of three types. It may be a linear polarization, it may be elliptical, it may be circular. As we know, the linear and circular are the special case of elliptical. Okay, and generally we should have an idea why, what is the need of circular polarization. Because what happens when we use to go, there is a transmitter and there is a receiver. That in the last lecture, one of our expert already told about that, there is a multipath fading. Okay, so because when we just think about the communication, definitely it will be inside the city. Okay, and once it is inside the city, what happens, there will be a lot of obstacles will be there, tall buildings will be there, some vehicles will be there. So what happens when the signal transmits from one antenna to another antenna, or from the transmitter to the receiver, definitely it will be reflected back. Okay, it will travel through different paths to the receiver. So what happens when it travels to different paths, so in that case, the phase will be changing. The phase will change, and signal strength may be lost. All these things may happen. Okay, but in case of circular polarization, okay, so those problems can be avoided. If the antenna is circularly polarized, it can avoid easily, very easily, the multipath fading. And multipath fading, this is what I told. Then there is a chance that antenna misalignment, as we know that when we are transmitting a signal between two transmitter or receiver, sometimes if the receiver antenna is disoriented or misaligned, so the signal is get lost. But in case the circular polarization, even the antenna alignment is changed by some little bit degree or something, okay, so but it can receive. Or sometimes the if the receiver antenna is movable in different direction, phi and theta direction, so in that case, if the antenna is circularly polarized, it can, it can use, it can transmit and receive the signal without any disturbance or without any signal loss. And also polarization losses, as I told, when it transmits to different path and all these things, definitely there will be some polarization losses. But in case our antenna is circularly polarized, so these three problems can be avoided easily. And of course, when the nowadays whatever the antennas, if the antennas are circularly polarized, then those antennas considered as the one of the best performing antenna, because they can receive the signal at any I mean at any position, at any direction, at any alignment. Okay, so this, that is why the circular polarization is very much important for one antenna. So we also thought up about designing some antenna that can use, because if you see, look at the literature, we of course will find a lot of work that has been done on circular polarization for DRA case. But we think, but the thing is that always it is challenging to find the circular polarization using single field, because there are different techniques, like we can use, we can ensure circular polarization in dielectric resonator antenna by using single field, by using dual field, by using different anti DRA shape also. Okay, because sometimes those things looks, I'm not saying that those are bad, but sometimes that becomes the DRA fabrication and all these things. If you just go for different kind of DRA shape, that may be difficult for fabrication. But in that from that point of view, there is advantage for using single field. In the single feed, what we did here, we can see the antenna structure is very simple. We have if we just look at here, the antenna structure is very simple. This is nothing but a slot coupled DRA, and this is nothing but, this is the ground plane. So I mean the back side, not ground plane. This is the ground plane, and this is the feed, and these two are the parasitic sets. Okay. So how did we develop this work? First, what we did, first we designed the ground plane one, that is on this one. Okay. What is ground plane one means? It's exactly not exactly ground plane one, but we just given the name like that. So first we used a field, okay, that is nothing but a simple field. Then what we did in the second structure, we did the, you just named it as ground plane two, where we put a set of rectangular copper sheets that's either side of the field line without disturbing the matching network. Yes, when we put all these things, we just look to the value of matching. If the matching is not being disturbed, then it's okay. Okay, and we found that the axial ratio that reduced to by around 6 dB. Okay, but as we know, the axial ratio, unless it is not below 3 dB line, we can't assume this is as a circular polarized. Okay, so what we did again, we started designing, restructuring that parasitic seeds that we given as a name of ground plane 3. We can see how did we do that. We just took an elliptical shape and we removed some part of that, so that we can form a parasitic shape, like taper shaped parasitic shapes. Okay, so by doing that, we found that it is able to create out of phase excitation inside the GRA. As a result, the waves that comes out, that becomes circularly polarized, because that also being verified by checking the axial ratio, whether that is below 3 dB or not. This work was published in the year of 2017, and we can see here the detailed performance is shown here. If we just look, this is the result, how the ground plane, this was the normal case. Okay, this is the in when we use the ground plane 2, I mean the rectangular parasitic seeds, then it of course it reduced around 3 dB. I mean that is this, sorry, it's reduced around 2 dB from this place to this place. And when we did its parasitic, I mean tapered shape, excuse me, so we found that the axial ratio that comes much below 3 dB, and that ensures circular polarization. And in the same case, in the same time, if we look at the performance of H11 and the gain, and we find there is a very rare changes. So that is not the, I mean, this putting and placement of these parasitic seeds, this don't affect the S11 performance and gain performance. It affects, but it is not that much significant changes. So we can use this technique for ensuring circular polarization in any kind of DRA. And the detail of the bandwidth we can see here. The detail of the bandwidth, if we look at here, the bandwidth is almost remains unchanged. The total bandwidth, percentage bandwidth remains unchanged or very little bit changed. There is no issue. And the gain also, if we look at here, gain is bit reduced as compared to the standard one. If the standard one, the first technique that gives 5.8, but there is no axial ratio. The second case, we got around 5.78, also no axial ratio, because here it was around 6 dB, the axial ratio. So it was not circular polarization. The third case, we can see that the performance is okay. I mean, the gain is reduced around 0.1 dB, but that is acceptable as we get the circular polarization, which is a very nice information here. And as already told you that these techniques are based on only single feed. Okay, then this is our measurement. We did the measurement, and we can say that it's okay. All the measurements are there. Is of course there is some changes, and that can be attributed to the fabrication loss, fabrication problems, and some unknown factors like air gap and all these things. This is another technique that we used. This is also a single feed technique. Okay, the single feed technique is as I already told you that we always focus for the single feed techniques, because single feed techniques becomes, we note, I mean, it's becomes simpler. The antenna becomes very simple. There is no complexity. So what we did here, we instead of taking it like cylindrical, we have used rectangular. Okay, first we designed, this is how we developed um, the spiral loop. Okay, this is a spiral loop. This is how we develop the spiral loop. Here we can see this different stages with different performances. Okay, and we can see that when we reach this state was able to create perfectly out of phase excitation, because the actual ratio was coming below 3 dB. That is this is the special case one. Other cases we don't find much. In stage 3 also we find, but if we just compare these two techniques, so we found that stage 3 is much better. Okay, and just move to the next one. How did we start it? First we used, so once we did that, once we finalize the spiral loop, first we put the spiral loop only one side, I mean on the right side, then we put it on the left side, then we put it on either side, and the result is shown below. We can see when we put it on the either side, when we put in the left and right side, we see that results are almost okay, it's just okay result. But the moment we put on the either side, we find it was producing dual resonance, and that was really very nice idea, because using a single feed and finding dual resonance. And if we'll just look at the axial ratio performance, also the axial ratio performance in case of the dual field, that is the red line we can see here, it is clearly showing that the axial ratio is below 3 dB. And using a single field, having achieving the dual resonance as well as dual axial ratio, that's really very good. But however, we accept here the one disadvantage was that the axial ratio bandwidth was not much better, but it was okay. But this work was okay, and it was because this work was quite novel. This I mean, this kind of using single feed and dual spiral feed, that was not. And this work maybe in future we may look into this work to enhance the bandwidth for the axial ratio. Okay, because this is not that much wider. This work was published in the IEEE Sensor Letters in 2018. This is also our work, and this is what the measurement, I mean the fabrication. Okay, and this is the measurement result. Measurement result was also bit disturbed, but that is acceptable. And the axial ratio we can see that is also acceptable. This is the figure that was taken inside an anechoic chamber during measurement. And this is the fabricated DRA. We can see because of some irregularity in the fabrication, there is little bit changes in the measurement results. And this is the stepwise comparison. I mean the stage 1, step 1, step 2, and step 3. How do we, what are the results? Okay, and in step 3 we can see it is clearly giving dual resonance here and here. And once we go for the measurement also, we find the dual band behavior was okay, and acceptable. And if we'll just look at the uh, literature, we find that this work was published by Lim. He's also one of our expert lecturer in day before yesterday. He was a speaker. So this is the work published by them, and what they have used a very nice technique that they just used a grounded parasitic patch. See, they have used a simple microstrip line, microstrip line with an annular slot, okay, and they just used here this is nothing but the grounded parasitic seed. The placement of this parasitic seed, they are able to ensure circular polarization. That means I mean axial ratio below 3 dB, okay, and this seems very simple technique that can be already they have done it for this antenna. So sometimes if someone requires for the application, for different application, they can use this technique for different bands, okay. I mean they have used at this band, so we can someone can think of about like co-band or higher band also. And if you look at the LSCP or RSCP, there is a good difference between the left I mean LSCP and RSCP in the both side. And of course this side that there is overlap, that won't be much that is not the big problem. But if you see in the both side area, there is much I mean very nice difference between the LSCP and RSCP. And if you look at here, also some authors have also produced some work that has been used to again using the single feed. Here they have used to printing two vertical metal strip on the surface of the cylindrical dielectric resonator. Okay, what they did here, they have not they have just used a microstrip line coupling. Okay, they have not used any slot or anything. But what they did here, they just put this place they just place the two vertical metal strip, and keep in mind placement of this vertical strip at any random position or ensure circular polarization, because we need to think about the angle, okay. And if you'll see here, this if you just look at here, the angle is around 45 degree. Here they have used the 45 degree, I mean this and this, okay. It should be 45 degree from the center, sorry, from the x-axis, this axis. If this is consider this is x-axis, it should be a 45 degree, okay. And that is how, and these two should be opposite to each other, so that it will generate axial ratio below 3 dB, and that is visible here, okay. And about the difference between the LSCP and RSCP in the both side, that is very nice. I think they have got the difference of around 20 dB in the both side for all the cases, okay. And that is very nice, and this technique can be used, this technique can be used for different frequency or different applications. And this is also very common technique that nowadays people use. This work was published in the year of 2003 by Huang and Ling. And if they have used a very popular technique, this is nothing but the slot technique, okay. And the slot technique, they have arranged the slots, four slots in the on the corner of the ground plane. As a result, that gives the axial ratio. And this movement of this, there are three graphs we can see. It is depend upon that the direct resonator radius and height ratio, okay. So I mean they have just clearly shown that the axial ratio or can be retuned, can be tuned, okay, can be tuned for any frequency, okay. I mean by using the same technique, they have clearly shown that how this axial ratio can be tuned for different frequency. And this is also a nice technique that published last I mean one of us that distinguished speaker here. If you just look at this work, they have clearly shown that they have very simple technique they have used. They have not used any hybrid DRA, just this simple rectangular shape DRA they have taken, and they've just made some modification on the feeding line, okay, feeding patch. If we look at here, how this W1, if you just look at here, this one, and here it is D. I mean this D, these two are the controlling parameter for ensuring circular polarization. See how beautifully they have designed, and this can be nice idea. And in case someone who wants to ensure wider band of this one, I mean they have shown if around uh, 1 GHz, 1 GHz acceleration bandwidth. In case you want, then you can just look into the uh, I mean the ratio of length to width and the length to height ratio of the dielectric resonator antenna. So if we just work on that, then we can again go for the wider bandwidth. But the important thing is that we need to look into these two parameters. There's W1 and D. Okay, this W1 and D, because this we can see that by controlling this one, how acceleration is beautifully controlled by using these two technique. Okay, and then the next one that comes using the multi-feed. Multi-feed means here they have used the two feeding techniques. Okay, and by using these two feeding technique, they have ensured, the authors have ensured TE11 TE11 mode and TE113 modes that excited and generate wide band circular polarization. This is, if you look at here, the bandwidth is really very nice. Okay, that is at the lower band, and of course, if it is lower band, the height maybe we need to compensate with the height of the DRA that may be larger. But this technique they have just used very simple, only 2 feet. Okay, and these are nothing but the strips. Okay, these are strips. These are not directly a probe. We can see it has a length and a width here. Okay, these are not the probe, but these are just the strips. They are put on the side wall of the rectangular DRA. And here the authors have used a very nice technique, and that maybe not, it's not difficult, but it's a bit tricky. This technique is a bit tricky. And if you look at here, they have used 2 feeds. This is one feed and this is another feed. Okay, there is one port, this is another port at the center, and one port on this side. And this port, this here also they have used a 80 ohm impedance line. They have used a 80 ohm impedance line that we need to look here how they have designed. You can see here how they have this is very much important at this point. Okay, because that mainly controls the impedance, otherwise there will be mismatch. Once there is the mismatch, again with the lost all these things. So what they have done exactly, the microstrip feed is technique used by circular polarized HEM11 del radiating mode with two mode and two orthogonal feeding microstrip lines of quadrature phase difference. Of course, once they are able to find the phase difference, okay, they can ensure circular polarization. But important thing is that we need to have this impedance behavior. We need to check this impedance behavior. Unless we don't able, because this seems bit tricky actually, bit tricky. We need to have patiently. We need to work on this. We need to work on this so that we can ensure circular polarization. And also in this, once we have the dual port, we need to check about the isolation. Okay, we need to look about the isolation. If each, I think this isolation that comes around this area, this is acceptable. This is bit somewhat it is acceptable, but it's okay. It's a nice work. This is also, I think, this work was done in 2009. And this is a quadrature strip fed CDRA. It's a nice structure, but looks for the beginners this may be a headache looking into the structure. But thing is that once we you are to master about creating the hybrid couplers. Okay, so for directly we should not, some the beginners should not directly go for this kind of design. Okay, once you are expert or once you are able to create the hybrid couplers, we need to, I mean you need to go for a lot of literature survey for designing the hybrid couplers. Okay, because couplers is it's a very big area. Once you know the coupler design, then we can easily design the 90-degree hybrid couplers. Okay, by pair of hybrid couplers, so that we can have the circular polarization. But thing is that we need to have some idea about hybrid couplers. Unless we don't have the idea about hybrid couplers, then we should think about other things, because hybrid couplers itself is a very nice idea and broad area. We need to look into that, those who wish to design. And but good thing is that here we can have a wider bandwidth even the lower frequency. Okay, and this is micro Wilkinson splitter. Okay, and this technique also we need to look into that. When we need to have a lot of idea about the circuit design and all these things. Okay, we need to do only literature, I mean only DRA idea. I want to help you. We need to look into this phase shifter, designing of the phase shifter and power divider. Okay, and once we have an idea about the phase shifter or power divider, this work is not much away from your wish. Okay, the thing is that here they have designed the 3 dB Wilkinson power divider. Okay, and a wideband 90-degree phase shifter. Okay, that gives good impedance matching, equal power splitting. By it splitting the equal power, which phase difference is 90-degree. Okay, so that is what the power divider generally does. Okay, so here we can see this is the port 1, and here they have used the Wilkinson power divider. Then they have used the phase shifter. This is nothing but the phase shifter part. This is the power divider part. Once they do this one, by using this one, actually what happens, as we see here, they have used the single port, the signal comes here, and the power equally get divided, 3 dB power divider. Okay, and once the power is here, we can see equal power splitting. I mean, the power gets divided into equally into two parts. One part goes in here, one part comes in this direction, and here this one comes in one phase. And here they have done this kind of technique. I mean, this arrangement, we can see it is a very straight line, and they have used this arrangement just to make a 90-degree phase shift. And once this go, let's say if it's going at 0, 190 degree, it is going at 90-degree phase, other phase. And these two port, when the input finally comes here, they are 90-degree out of phase. Okay, and once those two signals are out of phase, that will be able to create circular polarization. So here basically we need to think about three things. One, sorry, two part. One is Wilkins power divider that equally power divides the power. Then we need to think about the phase shifter that will shift the phase. This signal, one signal will be like this, normal. Like say it is, if it is 0, then this one will be 90-degree. However, either signal should be at 90-degree phase shift, so that they will be able to generate a 90-degree out of phase signal and circular polarization. This is what the antenna looks like from the cross-sectional view, and this is the performance we can see here. This is the gain performance, don't be confused. These two lines are nothing but the axial ratio performance. Okay, this is a very nice technique. And next to that, if you look into here, like we can find there are a lot. Some people have also used, instead of using like a different power splitter and all these things, people started using a hybrid DRs. Here, people have used they have taken a normal rectangular DRA and they changed. They did some arrangement. They introduced air gap and they able to find axial ratio. Here also, if you look into this figure, they have this here. If you see, the structure is very nice. I mean, looks simple, but thing is that we need to think of a lot of, we need to think and go for a lot of simulation to ensure that it can have axial ratio. And these are the very parameters that controls the axial ratio as well as the matching behavior. This on the left hand side, we can see they have used the stacking DRA, but the feeding, we can see they have used step safe conformal step that was able to generate axial ratio. Of course, the signal, I mean, the band was narrow, but this technique is good. Okay, then if someone wants to ensure a wider axial ratio, then can do something in the DRA shape. Okay, it's without disturbing the feeding technique. On the right hand side, we can see they have here also used, they have almost a step like, but they have used two half cylinders, like they have the metallic strips. They have used metallic strip used for the excitation, as well as they have placed another parasitic strip over here. Okay, which was very much helpful for ensuring circular polarization. Next is, if you'll see, these are also different modified DRS shapes they have used. We can see how they have changed the DRS shape here. Okay, they have two notches are truncated from this cylindrical DRA. I mean, this they have done like this, as well as in the slot. I mean, coupling. We can see how they have used. They have clearly shown here in the highlighted part. I mean, what are the different slots? They have used three slots. Okay, not only this is the main slot, and these two slots are mainly helpful for generating ensuring circular polarization. And the right hand side figure, we can see it is a circular polarization they have ensured, and they have rotated 45 degree with respect to side of the DRA. So if you'll just look at here, this is nothing but a stacking technique with increasing length and width of the DRA. So with increasing length and width of the DRA. And coupling technique is very simple, microstrip line slot coupling. But what they did here, they have rotated the DR at an angle of 45 degree. Okay, once they operated and once they rotate the angle at 45 degree, that creates a 90-degree phase difference. Okay, and because of that, they are able to get axial ratio below 3 dB. Then the next important parameter that comes, that is mutual coupling, because we know when we go for a multi-port, multi-input DRA and MIMO DRA, in this case, there is a very much important parameter that we need to look into, that is nothing but the isolation. If that, I mean, how there should be less power transmitted between these two DRA. For that technique, this technique was reported by Professor Guha in year 2008, and they have shown that by making a, they have just like They have reduced by using simple ring shape defected ground plane. Okay, by doing that, less power is transmitted between these two DRA, and that helps in enhancing the isolation. If you look at this figure also, this was done by the group of Kisk, okay, who was our speaker. And if you just, they have used a artificial magnetic conductor ground plane. The ground plane, they have nothing, I mean the DRS shape, they have not done anything, but they have used, instead of normal ground plane, they have used a artificial magnetic conductor, AMC ground plane, that helps in achieving isolation. So these techniques are mainly used for achieving isolation. Okay, isolation is nothing but mutual coupling, means how much power is transmitted mutually between the two elements. Okay, to improve that isolation, or we can say to reduce mutual coupling, we can have different techniques like that I showed previous slide and this slide. Then looks into the different applications of DRA. If we look at DRA history or DRA literature, we can have an idea that DRA has been used for different applications. That starts from microwave band to from different technologies, and sometimes they target for different frequency, and sometimes they target for millimeter wave. If we look into the figures, like this clearly tells that this, if we just look at the C band, it can be, people have shown that antenna can be used for C band applications. They have clearly shown that how they have used the hybrid DRA. They have taken the normal DRA, then have changed the DRA to different shapes, and they are able to achieve C band 31% bandwidth is 7.2. So normally, if you just look at here, I mean, these ideas just give a clear information that DRA can be used. I mean, DRA can be scaled off, can be designed for different frequency bands. Okay, once it reaches a different frequency band, we can tell that the other parameters can be ensured by different techniques. Like if someone wants to wish to enhance the gain, they can use the technique that we have shown, that I just showed earlier. If someone wishes to ensure high gain, they can also use the different techniques for high gain. You can see here they have used the step patch technique with intermediate substrate that can be applicable in X band. It's not only one structure. I have just given for an example. I have taken those structures. Okay, and there are a lot of paper we can find that been proposed for X band applications. Here on the right hand side, we can see they have also used the three triangular GRAs with a probe coupling technique they have used, and that can be used for also for X band. So also antennas also have been proposed for different, I mean different sets for co-band applications. Okay, so as we see that it was operating at 14.2, and here also they have used the cross slot technique with the cylindrical. Okay, this is a very simple technique, but thing is that once we move into the higher frequency, of course the antenna size will be less. That we need to look into, because that may be a problem when we go for higher frequency, like a K band and W band. If you see here, they have used the horn, because generally at this frequency the gain is expected to be high. That's why they have used the horn technique, okay, to enhance the gain. And the antenna was operated at K band operation, K band frequency range. So this is also a antenna that is that they have used the CPW feeding technique, okay, for W band application. And of course, when we go for the higher band, higher frequency, as we know, though, as antenna size becomes smaller, in that case, the fabrication of this DRA become difficult. Unless normally, like blindly, we should not move into for application for W band application design, because unless until we don't have the proper fabrication facilities, we should look into that. Okay, I'm not discouraging, okay, but I'm just giving information that we are just finalizing, we are giving a lot of time and knowledge, but at the final stage we are not able to fabricate that all these things, that sometimes goes vain. So this is also, if you look at here, people have used the WLAN application. This is a very popular application, as we know, that operates at 2.4 to 2.484. And on the right hand side also we can see they have used the three port DRA. Okay, I mean there are three port DRA where, yes, there are three port also. They have compared, they have shown the clear information about the isolation that is below 20 dB. I mean the isolation between these and the ports are good, and that can be applicable for WLAN in 5 gigahertz range. And this is also WiMAX application. These are also very popular applications, and we can use that. They have used here, they just wanted to have a better gain. That's all. That's why they have used the ground plane here. We can see metal plates. Two metal plates are attached to the edge of the ground plane. Here they have attached the metal plates. It just works like a bidirectional antenna, because that's why they have used this kind of plates. Okay. On the right hand side also they have used the same antenna for 3.5 gigahertz application. So this is very simple. So idea behind showing all this technique is that if we look into the DRA, most of the people think DRA may not be that much matured antenna, because this gives the idea that DRA can be used for any application. It can be designed, it can be scaled for any frequency. It may be lower band, it may be higher frequency, wherever the DRA can be designed. They can be designed to achieve the frequency range. But thing is that we need to look into the fabrication facilities. That sometimes becomes a big headache for us. And even if you see, there have been reported for medical application and sensing application also. On the left hand side, they have used for sensing application. On the right hand side, they have used for medical application. That was for detection of breast tissue. I mean the breast cancer case. They have used two antennas. Okay, and once the transmit and reception upon this one, they have also used the MATLAB coding to find all these values so that they can detect the size of the tumor. Okay, so even if you see, there is a very nice future. I mean, a very nice future scope in DRA. As a whole, we can conclude my presentation that DRA can be considered as much as possible solution for modern wireless communication systems. Okay, there is. It seems the papers, I mean, the literature shows that it can be used as a uh, for modern wireless communication. It can be suitably used for microwave as well as millimeter frequency bands, because it has very less loss even at higher frequency. As operating frequency continues to rise, DRA will become much more useful. Okay, that is because of the low loss characteristics, small size by factor of epsilon r upon root. That gives upon the low loss. It offer more degrees of freedom for hybrid integration. Okay, that is also a nice thing that I told, that DRA has been popular because of its the more degree of freedom. Okay, because it has length, width, as well as sometimes radius, and sometimes permittivity, relative permittivity. All these things adds more degrees of freedom to the DRA, which we rarely find in other antennas. And of course, we need to develop integration techniques for fabrication. Okay, that also a very nice thing that we need to look about the integration technique for fabrication, because fabrication is a major part for antenna work. Okay, so this is my work conclusion. If you have any queries, you can ask me. Otherwise, if later if you want to speak to me, you can also contact me on my mail IDs. And this QR codes I've given. Sometimes I design some antennas and put the design technique on YouTube also. You can find. You can just take a picture of this one. You can scan the QR code from YouTube or in my website on the right hand side. This one. So this may be helpful for you people, those for beginners. And if any queries, please let me know, sir.
Thank you very much, Dr. Sonik Kiran, for your informative session delivery covering different techniques for creating circular polarization in DRAs, followed by different application domain for dielectric resonator antennas. Quickly, I'm passing on 1 2 queries because next
Yes, sir.
speaker is in queue. I
Yes, sir.
cannot
Please.
hold him more.
Sure, sir.
How
Sure, sure.
how we can ensure that reflected signal will enhance the gain and it will not decrease the overall gain?
See, most of all, if you'll just look at the radiation pattern that I think I forgot to produce here, okay, even the reflected waves are being transmitted, or that is helpful in enhancing the gain. We can directly check it from the radiation pattern. We should not think about anything. Just look at the radiation pattern. We have a clear idea that it's enhancing the gain.
Okay. The next query is, what can be the disadvantage of dual fed circularly polarized DRA apart from their complex structure?
Okay, when we you go for dual threaded, actually we need to have like external circuit, external power divider circuit. Sometimes, if you have the normal dual port, if you are using the like Wilkinson power divider, then that is okay. But in case we are using two independent feeds, then we need to use an external power divider circuit. That makes the system again clumsy.
Okay. With this, thank you once again for being with us in 2 different sessions. And before saying bye-bye, I invite you to attend the valedictory function at 9:30 p.m.
Sure,
today.
sure.
Okay.
Th- Thank you
Okay.
very much,
Bye.
sir, for inviting me and giving
Thank
chance
you.
to share my knowledge with the people. Thank you. Thank you very much. Thank you all the viewers. Thank you.
Okay. You stop sharing.
Yes, sir. I'm just stopping sharing.
Good morning, Professor Antar. Sir, you unmute yourself. Your microphone is mute. You unmute yourself.
Good morning. You can hear me now?
Yes, sir. We can hear you. How,
Yeah,
how are you? How are you? How the things are
yeah.
going on
Fine,
in Kingston?
fine. Yeah. It's a bit snowy here, but you guys have nice weather. So
Okay,
yeah,
okay.
that was a good talk, Sunny. It's wonderful.
Yes, sir. Yes, sir. Can we start the session?
Yes, if you
Okay, okay.
just let me
Yes.
share the
Yes, please.
screen.
Good evening, Enter sir. Good morning, Enter sir. I'm Sonik
Morning.
here.
So Sonic Kiran, our PhD scholar.
Yes,
Presently, he is working as postdoc in Southern University of Science Technology, China.
where is that in China?
Yeah.
Yes, sir.
Yeah. Well, that was a very good presentation, Sunny. It's wonderful. Yeah.
Yes, yes. That
Can you
that
see my
that,
screen?
that is
Can
because
you?
of your blessing, sir.
Yes, sir. Yes.
Oh, thank you.
Time
Thank
to
you. You're
time,
very kind.
time to time, we directly or indirectly contacted when he was doing PhD here at NIT Silchar.
Yes, sir.
Yeah, that's wonderful.
Yes.
Can you see my screen there?
No, sir. You start presenting. You click on present now option, bottom right corner, bottom
Yeah.
right.
Okay. Mhm. Bottom right.
One icon is there, present now.
Okay, I did that.
Then select screen, entire screen. Select entire screen.
That's what I did. So can you see it now?
No. You are not clicked on that present now. If it is clicked, then select the screen, entire screen.
I did actually, but mm, okay. Somehow I'm not getting back to.
Have you clicked that icon, present now?
Yes, I did.
Then one window will come. You need to select that window in the
Okay,
screen.
so
In mid part of your screen, there will be one window. You
no,
select.
I'm not getting the controls now that I had before. So let me. So I will go on the present now.
Okay.
Entire screen.
Yeah.
So you see.
Entire screen. Then click
So
on
there,
that.
so
You
then
see
there
it
will be
now?
small. So when we click on entire screen, you will find a small window in the screen.
Okay,
In that,
let me go again. Present now your entire screen.
Yeah.
yes.
Yeah.
So there will be a small window. Inside the window, you select on the picture where it is showing the screen. Click on that, then share.
Uh, you see it now? Could you share it?
Uh, uh,
You
I think yes. Now it
Yes,
is
yes.
coming. Yes, sir.
Okay.
Yes, sir. Now make it slideshow. Yes, sir. Okay.
You see my screen now? Huh?
Yeah, yeah. We can see. Sir, on bottom side, one icon is there. You hide that icon. Not stop. Hide that icon on bottom side. Yes.
Hi. I say hi.
Yes, yes,
Hi.
yes. Yes, hide this one. Okay, now it is okay. Uh, you please allow me to formally introduce before the participants.
Yes, right.
Okay,
Please
okay.
go ahead, but don't take half of my time. Okay.
Okay, sir. Very quickly.
Okay.
It is my humble honor and distinct privilege to welcome Professor Yaya Antar, belonging to Royal Military College of Canada and Queen's University, Canada, as the next and last speaker of this 5-day ongoing Indo-Canada course on dielectric resonators and its application. Professor Yaya Antar received his BSc degree in 1966 from Alexandria University, Alexandria, Egypt, and MSc and PhD degrees from University of Manitoba, Canada in 1971 and 75 respectively, all in electrical engineering. In 1977, he held a Government of Canada visiting fellowship at the Communication Research Center in Ottawa, Canada, and in May 1979, he joined the Division of Electrical Engineering at the National Research Council of Canada. In November 87, he joined the Department of Electrical Engineering, Electrical and Computer Engineering at Royal Military College of Canada, where he has held the position of professor since 1990s. And he has cross-appointed professor at Queen's University in Kingston, Canada. He has authored and co-authored around 275 journal papers, several books and book chapters, and over 475 refereed conference papers, holds several patents, has chaired several national and international conferences, and has given plenary talks at many conferences of repute. He has supervised and co-supervised over 90 PhD and MSc theses at Royal Military College of Canada and at Queen's University, several of which have received the Governor General of Canada Gold Medal Award, the outstanding PhD thesis of the Division of Applied Science, as well as many best papers in major international symposia. He served as the chair of Canadian National Commission of RC 1999 to 2008, Commission B 1993 to 99. Dr. Antar is a life fellow of the IEEE, a fellow of the Engineering Institute of Canada, a fellow of the Electromagnetic Academy, and a fellow of RC, International Union of Radio Science. He serves as an associate editor of many IEEE and IT journals and as an IEEE APS distinguished lecturer. In May 2002, he was awarded a Tier 1 Canada Research Chair in Electromagnetic Engineering, where he has which has been renewed in 2016. In 2003, he was awarded Royal Military College of Canada Excellence in Research Prize and RMCC Class of 1965 Technical Excellence Award in 2012. He was elected by the RC Board as Vice President in August 2008 and in 2014 and to the IEEE APS ADCOM in 2009. Presently, he is President-elect of IEEE Antennas and Propagation Society for the year 2020. On January 31st, 2011, he was appointed member of the Canadian Defence Advisory Board of the Canadian Department of National Defence. In October 2012, he received the Queen's Diamond Jubilee Medal from the Governor General of Canada in recognition for his contribution to Canada. He is the recipient of the 2014 IEEE Canada RA Fessenden Silver Medal for groundbreaking contribution to electromagnetics and communication. And in 2015, IEEE Canada GM Hem Outstanding Engineering Education Award. In 2015, he received the Royal Military College of Canada Cohen Prize for Excellence in Research. He is the recipient of the IEEE Antennas and Propagation Society prestigious Chen Totai Distinguished Educator Award for 2017. Several things I have skipped from the biography available to me because of shortage of time. For that, I apologize from Professor Antar. And with this, I invite Professor Antar to start the presentation.
Thank you very much, Taimur, and I thank you all for coming to the talk and so on. I also would like to thank the organizers, the Institute and the University of Delhi, and thank all of my colleagues who participated in that and given very interesting talks, including the last one I just heard. And I am really pleased to be able to talk to you, and honored to be the last speaker. So I would share with you quite a bit of my experience in the topic and otherwise. And as you can see from what Taimur said about me, I've been around for too long, maybe far too long, but in the process, I learned a lot and keep learning and so on. And based on what I have seen here, I see there is quite a bit of future ahead of us for interesting work and so on. And if I just may take on a different hat for a second, Taimur mentioned that I'm the president-elect for the AP Society, and I'm going to be the president starting January. I don't know how many of you are members of this, of the Antenna Propagation Society, but when I was young, and that was a long time ago, I doubted if I should join and so on, but I'd have to admit that since I joined the society in the early 70s, which was also a long time ago, I learned a lot, and I encourage you to learn the society. It offers quite a bit of resources in terms of not only publications, but website that has courses, education, opportunities for conference and so on. So I invite you all to be active in this. And just to give you an idea about the volume of the society, if you look at the AP Society, which is one of the biggest societies of the 38 ITV, you notice we have quite a number of members there. And actually, more than 1,000 of those are in India. And again, as I said, I encourage the younger guys to join and check the website of the society, and you will see the resources there that are available and to continue to be available and very active. So please, be active in that. And as I say, as president-elect and the president next year, I invite you all to give me feedback and make requests. And we all think that the future of the society and the future area lies into more of the getting more of you younger guys, and we're getting old, so you are the ones who will be carrying the flag. So I encourage you to do that. Now I move on to the topic of the and as I said, the just take you a bit of history. The area of the electric resonator is, though it sees too many papers and so on, but it's actually relatively new. And I remember in late 1988, 89, when there was only the group at Houston and the group at Mississippi, and we got involved with it. And I remember the very first basic antennas, and when I looked at the electric resonators, and one of the speakers earlier, a couple of days ago, was Dr. Kashk, and we actually took some dielectrics and started playing with it and so on. And well, we had the first radiation, first slot coupled and mini ferris. So did quite a bit of work on that, and most of the speakers before me talked about more recent work and so on. So what I'm going to do in my talk here, give you a bit of uh, general ideas about the basics, which you have seen before, I'm sure. Also, give you some new observations on some of the work that might not have been covered, like including hybrid antennas and so on, and discuss some of the new things and the new challenges that could be there. And one of the big challenges, I think, that was mentioned by the last speaker is the fabrication. And this is a big challenge, and I think there are, few ways of getting new ways of fabricating those things, and at the same time taking advantage of the potential of DRE. So why this is basically some of the topics I'll talk about. So I'll talk about some of the fundamentals again, review some of it quickly, talk about the various techniques for bandwidth enhancement, and then this is something I'll talk about the hybrid DRE. And what I mean by hybrid DRE here is basically the following. Can you use DRE with antennas or other antennas to achieve some performance that you cannot achieve with either alone? How to use it to also use to again, I'm sure you have seen some of the arrays and some of the what I call recent development may not be as recent as when I prepared that, but it will touch on some of that. So let us look at dielectrics, and dielectrics have been around for a long time. They have been used in circuits and so on, but mainly if you go back to the history of dielectrics and so on, but they were used mainly as energy storage devices, not energy radiating devices. So these are some of the milestones of the use of dielectrics, and you can see that quite a bit of it goes back to the early days in microwave theory and technique society as well. And remember reading those papers by the lead Van Bledel, and we still didn't know at that time what to make of dielectric resonators. Well, it's the idea there. If you have a high dielectric constant and you have a wave inside, so basically the wave gets trapped here because you have a reflection coefficient. Epsilon is very high, so you have a reflection coefficient that's close to 1. So this is the way that we thought about it, that the field could be actually trapped inside those resonators. Now, these some of the shapes that have been considered during the literature, and I'm sure you have seen some of those shapes in some of the talks and so on, but basically, this is one of the advantages that you can actually play with the shapes and play with the concentration of the fields inside, basically play with the modes. First recorded antenna was basically Stuart Long, and that still was quite a bit of achievement at that time, when actually Stuart Long took some time off and worked for the US Army and developed that very first antennas. And since then, there has been quite a bit of work on that. Anybody who wants to start in the literature, well, there are few books, and I'm sure there are some that came on there, but you can see the volume of literature and so on. So if somebody wants to know, I could learn a bit about the basics. This used to be a good book to start with. Or this is when the very first book, the book by Aldo Batusa from CRC Canada here is also in the basics. There is more into the new antennas, and as I said, some of the speakers before might have had more contribution that I did not include here. Why the electric resonators? Well, these are some of the properties, and I'm sure some of you have heard quite a bit about these things. But the main advantage is low loss. So high radiation efficiency if you can feed it right. So this is this is a type of radiation efficiency you can get. Inherently wide bandwidth because it has low Q. And if I don't know if you have seen higher frequencies, but there is some that go as low as this frequency, and some that have been designed that go as high as this frequency, and maybe more now. Well, there is no service waves, low mutual coupling, and you've seen some papers about that or some discussion about that. This is one big advantage, as you have seen, is the flexibility, different shapes. So you can actually do different shapes to do two things: to fit it with what you have, or to engineer some field configuration that will give you certain radiation properties, as you're going to see in some of the examples I'll show here. The size control, you can use various epsilons, so you can actually have bigger or smaller size. Well, this is a bit of a lie here. It's not easy, but you can integrate it with other devices, and I'll show you examples of that. Radiation characteristics, because you have more freedom in the modes and so on. And so on are the other advantages, as you see here, with the temperature and so on. Well, some of these disadvantages we are all familiar with. Up till now, there are still some unknown or unexplored aspects. Theoretical analysis used to be less developed. It's a bit more developed now. One is not as low profile as microburst antennas. It offers better advantages sometimes, but not as low profile. And this is obviously the big challenge that we talked about in the fabrication and in the integration, and that includes the machining of it. Well, I think this is all stuff for you now here. You know the resonant frequency dimensions depends on the value of epsilon. And this is one thing that can be excited in various modes. And basically, all the feed mechanisms that we use for microstrip and other integrated antennas can be used here. You can do mode engineering, you can use higher order modes here. And it is mounted on a ground plane, so you can take advantage of that by putting the electronics underneath, as you have seen in some of the presentation. Methods of analysis until that time, where you have some accurate methods, where you can have some closer analytical solution. Then this was the old model that we used before. And then obviously most of the work now is being done and now using numerical techniques. There could be some confusion in the literature here, but the type of modes, you can have TE, EM, or hybrid. And these are all explained in that. And you can see the mode notation here, as you've probably seen, M with the phi, N with the rho, and L plus delta. Delta, L could be 0, and delta is basically the height in the Z direction, and that could be varying depending on the frequency and so on. The first three modes of a cylindrical DRA, as you've seen here, you can see the various modes and see the radiation pattern. One is like electric dipole, one is magnetic dipole, and so on, and the various radiation patterns. So based on the radiation required, you can design these antennas. And as I said, you have lots of resonance modes, and the lowest with the IQ, you can use it. And one thing I remember when Dr. Keshkandai actually got first one of these and put it into a feed line and looked at. We have seen lots of resonances, but lots of resonance. There are modes that get excited but don't radiate, and modes that get excited and radiate. And you could feel about this, or you can have a feel about these things. Kaifas, and then his book showed the modes and the field configuration and so on, and you can look at these things in there and see the modes and the various modes, hybrid, 1-1 delta, and so on. So I'm not going to get into details in this, but this is a basic figure to show the size reduction, or actually they're not. This is microwave antenna, single antenna, and the DRA both designed to the same frequency. You can see the advantage here in real estate. Both have the same frequency because of epsilon. You have real less size here, or taking less size here. Compare that, and if you look at the properties of them, you can see the radius reduction, the reduction in the size, and so on. And most of all other parameters are pretty well the same, except bandwidth here. DRA has inherently higher bandwidth. It's about the same gain and so on, but higher. And I'm sure you have seen before, and you'll see some here that where the bandwidth enhancement here have has exceeded many designs. You can see the comparison between them for the various Q and the various modes, and DRE actually gives you quite a bit of freedom in the fact that you have more modes than anything. And this is basically the microstrip and the electric, and you could see the advantage of the bandwidth and radiation the same. Various geometries, and you can shape them in the way you want. And I'll just attract your attention to the shape at the bottom here, where we actually did that, and you'll see in, shortly why we varied this here. And this is basically one configuration that could give you circularly polarized wave with one feed, and that it's not easy to fabricate, but we've done it. Conventional feeding techniques, they're all the same. We could use advanced techniques. You've gone through some of these techniques, and as I said, you found in the literature. Just a bit of idea about the lowest and the highest frequency of operation. So this is actually the lowest frequency of operation that's used for radar application. The antenna here is used at 55 megahertz. And epsilon, that, well, we actually made from water, filled. I don't know if any of you saw this work in the UK. Until a few years ago, this was the highest one that was done in Taiwan, antenna designed at that 130 gigahertz. And you can imagine the size of the resonator at that frequency and so on. But these, as far as, a few years ago, these were the highest frequency. You might have seen some higher frequencies. Band widening techniques, you have seen some of the design here, so I'll go through quickly some of this. As I say, there will be a repetition here in reference to previous speakers, but you can use single element method to increase the bandwidth. You can use multiple DRA, and then the hybrid antennas here, where I will show you that you can actually have quite considerable bandwidth. So this is a summary of the techniques used for DRAs, single element. And as I said, you might have seen many examples of this here. Use geometries to tailor the shape of DRA, conical shapes, and so on. Introduce air gap, basically to lower the effect of the electric constant, and use parasitic elements to use more than one element or fractal DRA. These are some of the shapes. So basically what you're doing here, you're using air gaps, and the air gaps are made in a way that does not affect the field configuration and so on. So you're basically lowering the effect of the electric constant, and you can have increased bandwidth. This is one shape we did actually some time ago. And you can see from that configuration here, this is basically configuration. So it was cut this way, and this is a very simple geometry. It's not hard to fabricate. And there you actually get 50% bandwidth, which is quite a good bandwidth, seeing the simplicity of the design. So this is the antenna, and this is the feed here. And this antenna has about 8 dB gain, and you can actually use this for 4 So this is basically the bandwidth there, and you can use it at various frequencies here. And this antenna was built and it's being used, and you can see that the bands that it's being used at, and it's remarkable. You have actually quite a bit of good gain over all of these bands by just simple design here. You could not achieve this using a microstrip antenna that easily. Uh, this is the configuration that I was talking about, and this is to basically get circle polarization. And the idea here was basically taken that by doing this shape, you can actually change the field structure, and you have two modes that are orthogonal and can produce circle polarization. This was done first experimentally, and then using mode analysis and so on, would be able to actually do work on that. And the performance of this antenna you can see here is not bad, and especially the action ratio is not bad over that. So it has a reasonable gain, but it has good action ratio and so on, and for that comb shape design. Uh, there has been unconventional shapes. This is, I'm sure Dr. Keshk talked about that, and conical shapes. I'm not going to go on that. And then we used unconventional shapes, cone shaped, and so on to do mode engineering and get certain radiation characteristics. And you can see some of this work on the literature and various wide banding techniques. And this is an interesting antenna that I said is actually using water, and you can steer the water around, change the parameters. This is work in the UK. They didn't continue this work after that, it worked too much. But what I will take a bit of time here is still talking about hybrid antennas. And basically, when I say hybrid antennas, can use DR to an advantage based to improve on the performance of or mix basically metal and dielectric to get that. And here is a good example that we have done. Still, a very good example. And basically, the idea there is, can you use a DRA with a monopole combined to achieve properties that you could not achieve with one of them alone? And here is the situation. And you have a dielectric ring and a monopole. The common thing about these things is that if you take the monopole, this is basically the figure 8. If you take the radiation characteristics of this ring, it has the same configuration radiation pattern. So what would happen if you put them together? If you marry them together? So the idea here was basically that this is a monopole. It will do two functions: radiate in its own, a pattern similar to that. At the same time, it could be exciting the resonator, and the resonator will radiate in its own. So what happened when you combine the two radiation patterns? But what you do, you design this for one frequency operation, resonance frequency of the monopole, and design the ring for a different frequency. This is basically what you get here. So you have the monopole and the DR. And if you look at this curve here, this is the monopole by itself. So the blue curve here is basically the radiation pattern of the monopole by itself. If you design the radiator by itself, you'd actually have a different resonant frequency here. So this resonant frequency here is basically close to what the resonator would be. If you combine them together, you actually get this whole response here. So you're getting a huge bandwidth. You cover bandwidth or from all the way to here. And radiation characteristics is constant. And when we put them together, we actually found that there is a third resonance frequency here that came in. So ideally, if you design the monopole, you will have this here. If you design the resonator by itself, you will have this frequency close to 16.1. But we found that in between, there is a third resonance here. And the explanation for that third resonance was based on the fact that actually the presence of dielectric around the metallic monopole affects the electrical length of the monopole and produces a third resonance. And that led us to the way we found that was basically looking at the current distribution. And if you go into detail in that, you will find actually that the monopole is reduced in length at a third frequency. And this would give us guidelines for actually to design. So if you want to design an antenna that has about 300% bandwidth, you actually you go back here, you choose the frequency. So basically you want the bandwidth from here to there. So this, you choose the frequency of the monopole, you choose the frequency of the resonator, and use these design equations here, and will give you an antenna that actually is excited in this mode and cover 300 bandwidth. Now, this configuration was used for a monopole. I know I think Dr. Liang and the group at you might talk about using similar configuration using a a ring resonator and so on. But what this telling us here is that this hybrid techniques by using metal and the electric, you can actually achieve certain performance. Uh, in the past, we did something but we didn't pursue it, and this could be an area that would be considered for research, is actually take the resonator and print on it metallic structures and see if you can excite various modes using this kind of technique. And this is basically the fabricated antennas here. I just want to be careful about my time here. So this is the hybrid configuration to excite a new mode, and this is where I don't know if anybody talked about that, but the basic idea here is you can do quite a bit of mode engineering in electric resonators. Some of the modes you could excite, and some of the modes you might have difficulty in exciting. And this was one example here where the electric field of that mode is parallel to the ground plane. So if it's parallel to the ground plane, you can't really excite it as such because the field has to vanish here. So you can try to go around this as we did, and this work was Dr. Goha from Kolkata. And we actually used non-resonance microstrip structure here to excite the fields and spread it around. And we were able to use this not as a microstrip antenna, but this is an example of hybrid thing. This is actually like an exciter. So the field vanishes around the sphere, but around the microstrip itself, the field exists and can excite the required mode that is there. So this is basically the mode, and the mode has high gain and it has higher frequencies and so on. So the idea here is that you can do quite a bit of mode engineering around the resonator, freedom that you don't have with other structures. And as long as you understand the mode and understand the radiation properties, you can realize it and so on. Various shapes resonators. You can have more than resonators together to achieve certain characteristics. To build various antennas, you can find this in the literature, but it's composite, various shapes and so on. So that gives you an idea about again, as I said, the mode engineering. If you understand the characteristics of the modes and so on, you can build your antenna around to achieve certain things. This is one configuration where we actually used the DRA as a radiator and as a feed element to achieve high gain. And this is antenna that's a very simple antenna that we actually can achieve reasonable characteristics and quite a bit of gain. And I'll just show you the configuration. It's basically the old FFP period resonator. But so you have here a microstrip line, a slot, and then you're feeding a resonator. And you have a substrate and superstrate. And basically, the idea here is this resonator gets excited. So actually, it provides an easy way of feeding the structure. And with the substrate here and superstrate, you actually spread the aperture here. If you look at the aperture here, we're looking at the cards on the top and so on. You see, looking on top of it, you can see the DRA here. And this is basically the field around. And you extended the aperture. If you extend the aperture, you're actually going to have a bit of a high gain, and this is gives you the gain and the performance of this antenna. So using DRA in this or in similar situations could actually provide you with an easy way to design high gain antennas and so on. I'm not going to talk too much about arrays in my talk here because I'm sure you have seen it. So I'll just hand wave at some of them. You have planar, and this was done long time ago and still very effective. You have the Dr. Keshka, I'm sure, talked about some of that, and the various designs by various groups. Reflector array, done quite a bit of that, and this is actually work that's quite some time ago, but still good. And you can see this was experimental and theoretical work that was done. And now I'll just hint about some work that we did, and this is about integrated DRA. And the work started at Queen's University, and we're basically using DRA to integrate it on for system on chip and so on. So it's quite involved with the thing, but the idea there was that can you make the DRA using different ways? And the different ways is basically to make a powder and let the powder go through a certain process. And then that process, you can actually fabricate some resonators, deposit them on the chip, and so on. So the for on-chip antennas and so on, there's quite a bit of requirements on their size because you can't have a big real estate on the chip. So the dielectric resonator gives you an advantage in that because if you compare the size of the resonator with the microstrip antennas, obviously there is advantage of smaller real estate the resonator buys, so that gives you advantage there. So for on-chip configuration, there were designs using printed antennas and all of these things, but then, as I said, they have two disadvantages. One thing is the space; they take quite a bit of space. And the other disadvantage is the losses when you go to higher frequencies and so on. If you do a literature survey on these things, you find that there is actually quite a bit of need for some, and still, this was done a few years ago, and still there is a need for producing on-chip antennas. And I think Atif Shamim and his group did quite a bit of work on that, and the group at Georgia Tech and so on. But the one thing that I wanted to hand wave at here is the work we did at Queens, where we actually, these are some of the drawbacks of integrated antennas, as I just said in there. So what we did was actually use DRA here because it gives you less ohmic loss, as I said, and the high permittivity can make the antenna smaller. So there is a process that this summarizes the process here. And I'm not going to go through, I don't have time to go through details, but it is documented in the literature. So basically, you grow the DRA on IC circuits, and then you do this at a lower temperature. You use optimization techniques and so on, and you actually build the antenna on the circuit. This is the process. It's more of a chemical process here, so it's actually done in the physics department at Queens. The process is explained in some of these references here, and as I said, this is some of the pictures of some of the resonators that were built, and it's done, as I say, at a temperature of 150 degrees Celsius, which you could actually use with some of the circuits. The normal process is used for ceramics was at around over 1,000 degrees Celsius. So this was a technique that was produced there, which is good. And you could actually put the the DRA on the chip, and this is some of the examples. You're actually using coplanar line to feed. And these are some of the designs we've done there, and you actually achieve good performance to some of them. The important thing here is, if you see in the next slide, this is basically the DRA here, and you get quite a good performance at this particular frequency. There are some inherent advantages here in using the DRA and the silicon, because basically the DRA attracts the field out of the silicon substrates, and you can see here, and the field is actually out, so you have less losses. So this is a process that was done, and as I say, I'm not going to talk about it too much here, but we have a design also that goes to higher frequency, and talking here about that high frequency, and the performance was good. The process is still under development at Queen's University, and there's quite a bit of effort that's going on that, and there has been quite a number of recent publications. You can check it on the size of the website at Queen's. Comparison with the previous work, the antennas that were done at Queen's University actually outperform those things. But the process is still not fully developed yet, but it actually offers a good potential for doing work at higher frequencies and so on. Some other work that was done in different places about this work here. So I'm referring it in the talk here. And I think Dr. Leong and his group reported on this using the hollow space here to put circuits. So this is another advantage. There is more recent developments and so on the various configurations DRA. I think you've seen some of this here, recent developments and DRA and so on. So I am not gonna talk too much, about some of these developments. What I wanna end here by saying that there is quite a bit of development in DRA. There is more to learn about it, and basically quite a bit about mode engineering, about integration with metallic antennas, and the most challenging thing I think would be the fabrication technique. If we can develop easy way to fabricate it, and especially at high frequencies and so on, DRAs are more tolerant to the dimensions and so on, and to the limitations. So I think there's quite a bit of development to to go ahead and for the future in there. So I think I'll stop here. I'm not going to have time to talk about you already talked about some of these things here. So I'll stop here, and I, again, I encourage you to seek other direction that, and I encourage you to be, involved with the Antennas Information Society. And thank you very much for your attention. And if you have any questions, I'll be glad to answer them. Thank you.
Thank you very much, sir, for a wonderful talk, starting from future scope in IEEE, then followed by different aspects of dielectric resonators, antennas development, and finally concluded with most recent development in DRS. Based on this presentation, I am having 2-3 queries from the participants. The first one is, would you suggest some reference for ultra-wideband circularly polarized DRA? Ultra-wideband circularly polarized DRA.
I think you're talking about ultra wideband. I showed a couple of designs of ultra wideband. So I think you can see those in the DRA chapter in the Antenna Engineering Handbook by John Balakis. I am not aware of the last couple of years what has been done, but the designs I talked about and so on, as I said, you can find more detail in the chapter, as I said, in the Antenna Engineering Handbook. I think Aldo Batos's book has some information about that as well. And there might be recent, I think Dr. Keshk did some designs in Concordia recently in that.
Okay. So next query from participant side is, which simulation software is best to observe different modes in DR?
Well, I think in most of our work we use the HFSS. Okay. Some use the CST, but in most of our work we use HFSS.
Okay. Sir, last query, like somewhere in your presentation, you have discussed one design of hybrid design of having one monopole with DR.
Yeah.
Then participant is having a query if both the antenna of one monopole and other DR independently working at 2 different frequencies, what will be the resultant frequency of this combination when we are taking the hybrid combination of monopole with DR, dielectric resonator antenna?
Yes, as I showed there, you have the monopole have its own resonant frequency, and the DRA have its own resonant frequency. So when you put them together, each of them works at its own resonant frequency. But the question is about the combined effect. What is happening with the combined effect is actually the resonator and the monopole, they play together and form a third resonant frequency. And that third resonant frequency is the reason for extending the bandwidth. And what is happening there, as I said, is you can think of the monopole being modified in electrical length because of the presence of the dielectric. And the curves I showed there showed the current on the monopole at the center frequency of the graph. So the effect there is that the monopole gets modified electrical length at another third resonant frequency. And this is why we have this 2.9 something bandwidth. And as I said, this configuration is actually available in literature, and it explained in detail in the chapter on the electric resonant antennas in the engineering antenna engineering handbook by John Balakis.
Okay. Sir, with this, we should conclude this one because some of the participants are having the query. Would you discuss something on like DRA advancement for RF energy harvesting? I think because of shortage of time, it is not possible to enter into that part. And last of your presentation was about to that. Better like later on some other occasions, we will discuss that thing.
Yeah, yeah. I'm referring you to the work of your also your Indian colleagues
Yeah.
in ISRO, Dr. Chinmoy Saha, and so on. So this is, if anybody is interested in that, I could provide references.
Yeah.
Reference.
Okay. With this, I must say thank you very much to Professor Antar. In spite of his quite hectic schedule, he has spared 1 hour for us for this ongoing Indo-Canada webinar course. And with this, I thank you once
Well,
again to you.
I
With it,
thank you all. I thank you all for your
yes,
attention.
Asant sir, with the request that you come again around 11 a.m. as per your time for valedictory session, if possible. For a couple
Yeah,
of minutes, you should please come again to grace the session, valedictory session.
yeah, it will be my pleasure, definitely.
It will be around 11 a.m. as per your time zone.
Yeah.
Okay.
Okay. Thank you.
Okay. Till then, you can have some rest or. Uh,
You too can have some rest from me. So.
Thank you, sir. Thank you. You
Okay.
can stop the presentation.
Stop now.
Okay. Yes, yes, yes.
Okay.
Is this screen visible to the participants and speakers too? Now, as per the guidelines already mentioned in that schedule, that we need to conduct one MCQ test based on all the presentation of around 14 presentation which we have covered in that MCQ test. The duration for that one is 45 minutes and total 50 questions you are having, and the like maximum marks for that paper is 100. We have to give the marks for out of 100, and the question paper has already been sent to your registered email. Participants can take that one from your email, and shortly it will also be shared here in that YouTube chat box. That is up to you. Okay, and just give me a few seconds. सर 2-3 मिनट के लिए हार्डली, क्योंकि ज्यादा नहीं लगेगा। बीच में आप 9:45 के आसपास ज्वाइन कर लीजिए, 5-7-10 मिनट तक क्लास चलता हुआ होगा, उसी बीच में 1-2 मिनट बोल लेना। हाँ सर, अभी कंसेंट तो दिया है, एक्सेप्ट यूनिवर्सिटी ऑफ हांगकांग, क्योंकि वहाँ टाइम डिफरेंस हमसे वो 2.5 घंटे आगे है ना। तो Good morning, Professor Kishk, and welcome to this valedictory session.
Do you hear me?
Hope you are good there.
I'm fine. Do you hear me?
Yes, I can hear
Okay,
you.
good.
Okay. Thank you very much for sparing times for this valedictory session. Good evening and welcome Professor K.L. Vaishnav for this valedictory session.
Very good evening. Very good evening. Huh?
Within,
Very
within
good that really you are end of the program.
yes, sir.
Yeah, I can see Professor Ahmed Kish. Good evening, sir. Ahmed, sir.
Professor Kishk, your microphone is mute.
Yeah,
Hi,
Professor
how are
Gangadhar
you?
also. Very good. Yeah, evening. Maybe for you, good morning.
Yeah,
Professor SP Gangwar. Professor, very good evening. Professor Gangwar. Yeah, now Antar sir has joined, na?
He will be joining shortly. Earlier
he
he has
joined.
no, he has already joined, but right now he is not before the screen. Shortly he will be come back because just now he has delivered his talk and he has taken a couple of minutes.
Yeah, Ali sir has joined.
Good evening, Professor M. Ali Ahmed sir.
I was muted. Sorry. Good evening, sir. Good evening.
Welcome you for this valedictory session.
Yeah, I was muted. So, Vaishnav sir, how are you?
Very good. Ali sir, then really one by one event. Finally, Taimur has really concluding the events. 5 days hectic schedule. Inviting so many experts.
Completed. Professor Antar is here now.
Taimur, audio is, I think, there's a break in the audio for Ali sir, na?
I'm not
Is
getting
it?
breaking.
Audio is
Yeah.
breaking. Lida, maybe.
Audio
Is
is
it
breaking.
breaking?
Yeah,
My audio is breaking.
not
No,
your.
not your radio.
Now
What
it
is
is okay.
your
Ali, Ali. Now it
Okay.
is okay. Now it is okay.
Okay. Yeah, Antar. Professor Antar has joined, na? Professor Yahya Antar has joined.
Yes.
I think it is good morning to Professor Antar.
Right now, I think he is not on before the screen. Just now, he is. Yes, he will be joining shortly.
Okay. Sure. Then director sir will join, na? Oh, he's on the phone.
Hi, Professor Denedni. Good morning. Professor Tayyab Denedni, can you hear me?
Yeah, Taimur, Professor Antara Johan. Very good morning,
Yes, yes.
sir. Antar sir. Very good morning.
Good evening for you.
Right, right. Uh,
Good morning.
good morning,
Okay.
good morning.
Welcome, Professor Tayyo, for this valedictory session.
Good morning, Tayyip. How are you? I guess he's busy.
Yes, I think.
Yeah. This one.
Dr. Khan, yeah, our director sir will join, na?
Yes, sir. He's saying that within couple of seconds he is joining.
Okay,
That's why we are just waiting for him only.
okay, okay.
Hi, everybody. Good afternoon. You hear me well?
Yes.
Good morning, good afternoon, good evening.
Thank you very
Yeah,
much.
yeah, sir, you are audible. You are audible. Good morning, sir.
See, Dr. Kishk is
Good morning, Ahmed. Good morning, Yahya.
Hi, good morning,
And
Tayyip.
good afternoon for everybody in India.
Thank you, sir. Good afternoon to you as well.
Good evening, sir. Director sir.
Good evening, Director Sir, and welcome to this valedictory session.
Good evening and
Good
good
evening,
morning.
sir. Good evening.
Good evening and good morning to our colleagues from Queen's University, Canada, Professor Antar and Professor Kishk.
Yeah. Good evening, sir.
And Director Sir, can I proceed for valedictory session? Because we are
Yes,
just
yes,
waiting.
please.
Okay, sir. Thank you very much. Thank you. Hello, everyone. Myself, Dr. Taimur Khan, on the behalf of organizing committee, is going to start this valedictory session organized after successful completion of Indo-Canada Spark course on dielectric resonator and its application DRA-2020. Respected Director, Professor Shivaji Bandyopadhyay, Dean Research and Consultancy, Professor M. Ali Ahmad, Institute Coordinator Spark, Professor Upendra Kumar, Head of the Electronics and Communication Engineering Department, Professor K. L. Vaishnav, entire team of Spark project, all invited distinguished speakers, organizing team of DRA 2020, esteemed colleagues, friends, and dear participants. Good evening, good morning, and good afternoon to one and all present over here. On the behalf of organizing committee, I welcome you all for this valedictory session conducted after successfully completion of this 1 week long virtual webinar course on dielectric resonator antenna, dielectric resonator and its applications, DRA 2020, organized by National Institute of Technology in association with Delhi Technological University and Queen's University, and hosted by Department of Electronics and Communication Engineering, National Institute of Technology, Silchar. It has been a wonderful experience of organizing this 1 week long Indo-Canada webinar course, DRA 2020, in this ongoing global COVID-19 pandemic situation. Several new things several new things have been learned during the whole period of DRA 2020, how to use the digital platform for such a huge gathering effectively. The aim of this webinar course was to provide a common platform to the researchers working or wish to explore their research in the area of dielectric resonator and their different applications. The webinar course has addressed several fundamental concepts related to the recent development pertaining to dielectric resonators. At the same time, it has included in-depth discussions on various design challenges that are encountered in this field and their possible solutions. The webinar course has provided not only the essential knowledge but also a platform to the participants for exchanging their ideas and information with the respective distinguished speaker. Total 8 distinguished speakers, including Professor Yahya Antar from Royal Military College of Canada, Professor Ahmed Akish from Concordia University, Canada, Professor Tayyib A. Denizny from University of Quebec, Canada, Professor Ben Liang from City University of Hong Kong, Dr. Soni Kiran Kumar Das from Southern University of Science and Technology, Shenzhen, China, Dr. Surendra Pal, Distinguished Scientist from ISRO Satellite Center, Bangalore, India, Professor Bhaskar Gupta from Jadavpur University, India, and Professor R.K. Gangwar from Indian Institute of Technology, Indian School of Mines, Dhanbad, India, have, have successfully delivered their talks in different expert areas. Now we would proceed for vote of thanks one by one. Honorable Director, entire team belonging to Spark project, invited distinguished speakers, organizing team of DRA 2020, esteemed colleagues, friends, and dear participants. I, the convener of the DRA 2020, deem it a great honor to propose the vote of thanks to all who has helped us in making this virtual webinar course such a resounding success. As a convener of this webinar course, first I would like to propose my vote of thanks to Ministry of Education, Government of India for funding this webinar course under ongoing Spark project. In the continuation, I must now mention my heartfelt thanks to our respected director, Professor Shivaji Bandyopadhyay, for giving us an exposure to conduct this webinar course. He has always been a source of motivation and an encouragement as well to do something new in the department for the overall development of the institute. Next, I would like to propose hearty vote of thanks to Dean Research and Consultancy, Professor M. Ali Ahmad, Institute Coordinator Spark, Professor Upendra Kumar, Chairperson of this webinar course, Professor K.L. Vaishnav, for extending their support for making this webinar course successful. Next, I would like to pass my warm welcome to the entire Spark team involved, especially Professor Yahya Antar as Foreign PI and Professor Frondorfer as Foreign Co-PI, both belonging to Queen's University, Kingston, Professor Ashok Day as Indian Co-PI belonging to Delhi Technological University, Delhi, and lastly myself, Dr. Taimur Khan, as Indian PI from National Institute of Technology, Silchar, whose collective efforts has made this webinar course possible. Next, my sincere gratitude to all the distinguished invited speakers from India and abroad, especially Professor Yahya Antar, Professor Ahmad Kesh, Professor Taib, Professor Ben Liang, Dr. Soni Kiran, Dr. Surendra Pal, Professor Bhaskar Gupta, and Professor R.K. Gangwar. Thank you all for accepting our invitation and agreed to share your knowledge with the young participant in their respective areas of expertise. As no program can become successful with a single person, so I extend my big thanks to the entire organizing team associated with DRA 2020, especially Dr. Ripon Patkiri, Dr. Naresh Babu, Dr. Suroj Kumar Vishwas, Dr. Partha Pakre, Dr. Ranjay Hajra, Mr. Manas Mahanta, Mr. Najmul, and our own student Dasri Surendra and Suman Modak, who managed different activities to this digital platform on which we all are connected this evening and was remain connected for the entire duration of 5 days of this webinar course. In last but not least, I extend my warmest welcome to all the participants belonging to different parts of globe, irrespective of different time zone, who have registered for this webinar course and enjoyed all the sessions and have made this webinar course a grand success. Next, feedback is very much important component to judge the success of any event. Keeping it in mind, I, on the behalf of organizing committee, would like to hear the overall participation, overall perception, starting from distinguished speaker then to registered participants. Keeping that in mind, it would be an honor for us to know the overall perception from the distinguished speaker. Uh, and anyone starting from like would be it will be honor for me if Professor Kish is say a few words about his own experience for the entire process of that 1 week long DRA 2020.
Thank you, Dr. Khan. I was really impressed by the organization of this course. Especially, it is a global-wide course with this large number of participants, more than 130 participants all over the world interested in dielectric resonator. And this is really a good example that I'd like to see it done for many different topics, not only related to antennas or to the microwave areas, but maybe other areas as well. And if it is organized by India or any other country, that is really a very good example for spreading the knowledge about our areas of expertise. Thank you for a successful short course.
Thank you, sir. Thank you very much. Next, it would be an honor for me to invite Professor Taib Dinidni to say a few words about his own experience.
Yeah, good afternoon and good morning for everybody. I think this is an excellent opportunity for many researchers, and I think it is a successful event that let people to gather and to learn a new topic about dielectric resonator antenna. And I think, as my colleague mentioned, Ahmed, we can replicate this formula for other topic or other field. But I think it's very, very excellent opportunity for researchers to gather and to learn and to discuss and to collaborate. And I hope maybe one day when if the COVID disappears, we can do it physically. That's it. And I think good luck for the next event. Thank you very much and have a nice day or have a good night.
Thank you. Thank you very much. In the speaker list, if Professor Gangwar is there, if Professor Gangwar has joined, then he may share his experience while delivering 2 different sessions in 2 different slots.
Yeah. Thank you very much, Professor Khan. And I would like to say that my experience is very, very quiet and encouraging. And I like the question and answer session where the students are very interesting and they are asking the questions which are very, you can say that is by seeing the questions, it is perfectly going to be said that they are liking the session and they are deeply involved in that kind of their lectures. Also, when I see the speakers list, I like that each and every person which are belonging to this particular topic, they are there. Those who are basically you consider that the top 10 people, if you are going to be see in this field, all you have collected in the same place. Give your one of the wonderful experience for me. I have also attended many lectures, and I find that it is wonderful things to get such kind of the program, so that each and everyone is basically going to be benefited. So I'm really thankful for you to conduct such kind of I can say that a program which is going to be useful for I can say that the students as well as your learned faculty colleagues who are just coming in this field. So thank you once again for this one.
Okay, thank you, Professor Gangwar. Now, I think keeping the time constraint in mind, I would like finally call upon Dr. Soni Kiran to say a few words about his own experience, as he is the alumni of NIT Silchar and I think youngest speaker in the list of speakers, youngest one.
The microphone, I think.
Your microphone is mute.
Thank you. Okay. I think it's really very great experience for me because I think Taimur sir has arranged, I mean, invited all the top people who are working in this dielectric resonator in antenna area to this short course. Really, honestly, I have been only reading those people's work on internet and on PDF file, but when I could see them physically, I mean, through online, it was a really great experience, and I just learned many things. And even thank you, sincere thanks to Taimur sir for inviting me to this prestigious platform and arranging such a course during this COVID-19 lockdown period. And it's a really wonderful experience. And sincere thanks to all the speakers also, like all senior professors, for sharing your sharing information with us. Thank you, Taimur sir, and thank you all the organizers.
Thank you all. Now the participants' feedback is also equally important. In the end of valedictory session, each registered participant has to submit online feedback. In addition, we have created a Google Meet platform for around 50 selected participants so that they may share their observation about this event DRA 2020. Quickly, it is not possible to call by name. If anybody is interested, then come forward to say few words about the whole week experience of this DRA 2020. Anyone from participant side? Anyone from participants? Okay. One participant is raising the hand. What's the problem?
Yeah.
Yes.
Good evening. Yeah. Good
Okay.
evening, sir. Yeah. Here, Amay Kadam from Mumbai. It's our privilege to listen to such great personalities or great sir in the field of antenna and dielectric resonator. Very well organized FDP. Thank you for your cooperation, and I enjoyed all the sessions. Thank you, sir.
Thank you. And anyone else? Next participants, come forward quickly.
Good evening, sir. Hi. Hello, sir.
It was such a delightful experience to attend this workshop. And actually, before joining this workshop, I was working on MIMO DRA, and I was stuck somewhere in for mutual coupling. So this workshop actually helped me to like get out of that get out of where I was stuck, and now I can move further in my research. Thank you so much.
Now last query from participant side. Last feedback. Yes, please. I think Nipun Mishra.
Yes, sir.
Yes, please.
Yeah, good evening to all. First of all, I would like to congratulate to organizer for organizing such a wonderful FDP on the dielectric resonator antenna. All the renowned person in dielectric resonator antenna are joined in this platform. So everybody will be benefited from these lectures and their experiences. So it was a very nice experience that all the big persons on dielectric resonator antenna have joined in this session. Thank you very much.
Thank you very much. Now the webinar course DRA 2020 is organized by NIT Silchar in association with DTU Delhi and Queen's University, Canada. I, on the behalf of Spark team, would like to invite Professor Yahya Antar to say a few words on the successful completion of this event, DRA 2020.
Can you hear me?
Yeah, we hear you well.
Yes.
Yeah. Well, thank you, Taimur, and I thank all of the team and Silchar and the ministry and so on. This has been a very good experience. I think the important thing here is, in spite of the COVID crisis and so on, managed to bring a big group together and uh, the young guys who participate in this and speakers from all over. I think on behalf of organizing committee, I thank everybody for that chance. And take home from here is a start. I don't think it should be the end of the process. I think that should give us a chance to network more, learn more. It's very hard to learn in 3 days or 4 days everything, but this should be a beginning to learn more and repeat more of these things. And I encourage the younger guys, students, so on, to be involved and not shy away and learn. And I'm hopeful that all of you will take the science and advance to new frontiers. And I echo again the words repeated by Dr. Fish and Dr. Ganedni that there's more to learn and keep active, get involved, and I think there should be more activities in that, joined with the conferences and so on. And again, I encourage you all to stay active with the community through seminars like this, through IEEE activities, and then as a publication, the education committee and so on. So thank you all. And this has been a wonderful experience. And thank you, Taimur, for going through all of this.
Thank you, sir. Thank you very much.
And
now,
and when I think when I was young, which was a long time ago, as I said, seeing this kind of activities could be inspiring, and look forward to more flourishing work and new ideas. Thank you.
okay, sir. Thank you. Thank you very much. Again, I would now invite Professor Ashok Dey from Delhi Technological University to say a few words as a vote of thanks if he has joined, because he was busy with some other meeting as he dropped a message to me. If he has joined, please, Professor Ashok Dey. No, I think. Okay, no problem. Then finally, I would take the pleasure to invite our Honorable Director, Professor Shivaji Bandyopadhyay, to say a few words on the successful completion of this webinar course.
Yeah, very good morning to Professor Antar, Professor Kish, Professor Denidni, and very good evening to my colleagues from India, including NIT Silchar, and wishing a very good day to all the participants across the globe who have joined this program. During this pandemic period, this particular Indo-Canadian Spark program has been organizing a number of programs. I remember welcoming Professor Antar in the webinar, online webinar a few months back. And I do wish that very soon the pandemic will be over and we'll be able to welcome the Professor Antar and his team, and as well as the set of distinguished speakers, including our Indian co-PI from DTU Delhi, Professor Ashok Dey, into the campus. And in future, I do believe that this relationship on this dielectric resonator or the Indo-Canadian Spark project will expand to an institutional relationships for a long time. And so when our students will be, say, attempting to go for MITEX scholarship, where they require a professor in Canada to accept them so that they can apply, I do believe that the relationship that has started with the Queen's University Canada, Concordia University Canada, and others, so that will expand into a relationship so that it will continue beyond the boundaries of the Spark program also. And from the feedback of the distinguished speakers, as well as some of the feedback from the participants on the chat box. I see that the program has been quite a success, and so everyone is wishing for a repeat of the webinar of this kind. Thank you all, and thank you for organizing such a networking program. So it has not only touched the subjects, but it has also touched the networking of people across the globe. Thank you all once again.
Thank you, sir. Thank you very much for your motivational words. Now, I would like to call upon Head of the EC Department, Dr. K.L. Vaishnav, to say a few words as a vote of thanks.
Thank you, Dr. Taimur. Very good morning, very good evening, and yeah, a very good afternoon to all. This is the second the Sparks activities that's already one activities happened, and this is the second, and we have seen the we have listened the comment from the experts as well as from the participants. It shows that really the event is very much successful, and as already our directors have already said that that's the relation today that we have started, it will go beyond the Spark also, because many of our students, UG as well as PG and PhD students, they look forward for research collaborations. And since we started this process, I hope so that Queen University, then City University, then University of Quebec, Canada, there will be great, I think, ventures for all of us, because we have a potential is that we have a strong young forces, and India is really the great potential that we have a strong working force, students with a lot of energy, and only we need to nurture them in a proper direction. I hope so that these collaborations, not only for the Queen University, we have seen in these workshops, we have many other faculty from different countries. We can have see Hong Kong University. We can see that the University of Duke in Canada. So there are many others, IIT, ISM Dhanbad. So that's a great opportunity for all of us, especially for the NRT Silchars. Taimurs and his group really invited so many speakers, and the platforms that's given to all of us. Not only the experts, we have so many participants also see there are also faculties, and one of our alumni, Dr. Shaunik Kiran, now in China, is a great opportunity for all of us also to extend our his support and collaborations in the direction of dielectric resonator, as this is a multidisciplinary area, and many people, electronics, mechanical, electrical, can join and have a great works toward the great cause of the society. With this, I look forward that these workshops will go beyond these Sparks, and beyond the Spark, we'll extend our hands for more collaborative works. So finally, I extend my heartfelt thanks to the entire team of Dr. Taimurs. And the backside, I seen that he has already shown some photographs of different faculties as well as our technical staff who are behind these online courses. One thing we are missing because of COVID-19, that many professors that's now we see just online, and we are missing their presence in the campus. We are expecting that once this COVID is over, we'll be expecting those professors at the NIT Silchars, and then really it will inspire our faculty as well as students, and will make more cordial relation to forward new projects and new collaborations. With this, thank you all. Thank you all. So over to Dr. Taimur.
Thank you, Professor Vishnav. Now coming to the final concluding remark, I, on the behalf of organizing committee of DRA 2020, thank you all once again for being with us in this valedictory session. And it has been really a great experience of using this digital platform in this ongoing COVID-19 pandemic situation. Now, before saying you all bye-bye, I would request to all the registered participants for submitting the overall feedback of DRA 2020. With this, I conclude myself, and bye to all. Good night, good morning, good afternoon to all of you. Be healthy and be safe. Thank you all for joining this valedictory session. Thank you all.
Thank you. Good night. Stay safe.
Thank you. Thank you all. Please.
Thank you. All right.
Thank you, sir.